The universe is vast, ancient, and full of mysteries, but is it also home to creatures the size of mountains, drifting through the void, or lurking in alien seas? Science fiction has long imagined titanic beings, from Star Wars space slugs to Dune's mighty sandworms, and even legendary kaiju like Godzilla. While these stories often stretch the limits of biology, they raise an intriguing question. Could truly enormous organisms exist somewhere in the cosmos, not just in fiction, but in fact? And if so, what environments might allow such giants to thrive? It's a fascinating topic in science, not just science fiction, and one we've explored before in episodes like space whales, void ecology, and giant space monsters. But today, we're going even bigger, because when it comes to life's potential in the universe, size might be limited only by imagination or physics. And even those limits might fall away in other universes with different physical constants, where creatures could exist with stars for hearts or entire galaxies as living, breathing organisms. So, grab a drink and a snack, give that like and subscribe button a smack, and let's dive headfirst into the colossal world of cosmic megafauna and megaflora. Before we can imagine massive life forms swimming through alien oceans, or drifting between the stars, we need to confront one of biology's most stubborn challenges, the so-called cube-square law. As creatures grow larger, their volume, and thus their mass, increases far faster than the strength of their bones or muscles. That's because volume scales the cube of size, while cross-sectional strength only grows with the square, much like an animal's surface area for skin or scales. On Earth, this dynamic explains why land animals face natural size limits. Their increasing mass eventually outpaces what their skeletons can support. Galileo noticed this centuries ago, observing that larger animals needed disproportionately bulkier bones just to hold themselves up. As a creature grows, its feet, ankles, and leg bones must become dramatically wider and stronger to bear the load. More and more of its mass gets devoted simply to bones and muscles for movement and support. Eventually, growth becomes self-defeating. A creature might reach a point where gaining 100 kilograms of body weight demands 99 kilograms of new muscle and bone just to move that added weight. Push it further and the cost tips over. Now it needs 101 kilograms of new structure to handle 100 kilograms of new bulk. At that point, your monster collapses under its own weight, if it ever evolves that far at all. Evolution, of course, tends to apply the brakes long before that. In short, big things get heavy fast, and there comes a point where the sheer weight of a creature becomes too much for it to support. This is why Earth's largest creatures today, like the blue whale, are aquatic, where water provides buoyancy and reduces the crushing strain of gravity. But what happens when we leave Earth behind? Could alien worlds with lighter gravity, denser atmospheres, or entirely different biochemistries allow life to grow far beyond anything we've ever seen? Could the universe hide creatures so vast, so alien, they blur the line between biology and landscape, or even cosmology? Let's find out. The limits of size in biology. The largest animals ever to live on Earth are the great whales, with the blue whale still reigning as the heavyweight champion, tipping the scale at around 200 tons. On land, the mighty sauropods of the Mesozoic were the biggest creatures to roam, yet even those long-necked giants rarely exceeded 80 tons. Someday we might uncover fossils of an even greater ancient leviathan, but Earth's creatures hit a ceiling for good reason. Size is a cruel master. That ceiling isn't set by biology alone, but by the unyielding grip of Earth's gravity, the chemistry of our atmosphere, and the long, slow march of evolution. Change any of those, alter gravity, swap in new materials for bones, or tweak metabolism, and suddenly life could scale up in ways we've barely imagined. In those alien settings, the giants of Earth's past might look small, their records easily shadowed by megafauna on distant worlds. One of the first bottlenecks in scaling up life is what you're made of. Earth's vertebrates rely on calcium phosphate for their bones, a material that strikes a balance between strength and lightness but hits its limits fast. Some species try chitin, like insects and crustaceans, but it's no magic fix. Yet on alien worlds, biology might have access to entirely different toolkits. Creatures could weave their skeletons from carbon composites, spin ultra-strong fibers like spider silk, or even incorporate metals, iron, titanium, or exotic bioceramics into their very bones. Imagine a creature with carbon nanotube ligaments or a skeleton laced with natural titanium, strength enough to carry mountains of flesh. But raw strength is not enough. Big bodies need big power. The blue whale gulps down tons of food daily just to keep going, and any alien giant faces the same metabolic arms race, something we contemplated in our Big Alien Theory episode. Some worlds might demand entirely new energy strategies. Why settle for oxygen and sugars when you could run on geothermal heat, or tap the radioactive heart of a planet itself? Out in the void, as we explored in Void Ecology, we even considered creatures with internal thermoelectric generators living out the heat of their surroundings, or biological reactors slowly burning radioactive materials they ingest. A walking, lumbering nuclear reactor, moving ponderously through the dark, its life measured not in heartbeats but in half-lives. Still, movement is the cruelest limiter of all. Gravity grinds giants down, forcing every step to be a battle against collapse. Legs, even titanic ones, eventually betray their owners. Some colossal creatures might abandon limbs altogether, slithering like sandworms to spread their weight, or sprout dozens, maybe hundreds of legs, turning themselves into slow-moving forests of muscle and bone, millipedes at a megascale. But physics cuts both ways. Lower gravity worlds or denser atmospheres offer strange new options. There, life might evolve to float, ballooning up vast gas bladders filled with hydrogen, helium, or methane, drifting lazily like living zeppelins. As we saw in space whales, some beings might even take that a step further, evolving into creatures that swim through skies or space itself, buoyed not by water or air, but by sheer engineering of biology. In the end, size is governed by a delicate dance of materials, metabolism, and environment. On Earth, that keeps even our greatest leviathans within certain bounds, but out there, across alien oceans, alien skies, or even the depths of interstellar space, those rules might stretch or break entirely. Somewhere in the universe, there could be creatures so vast they are not just animals but ecosystems, drifting worlds unto themselves. Cosmic megafauna in different environments. If there are titans among the stars, where do they sleep, feed, and grow? Life's potential size is written not just in its biology, but in the environment that shapes it. While Earth's gravity and atmosphere keep our giants modest, the cosmos offers far stranger arenas, alien seas, endless skies, and even the vacuum of space, where nature might sculpt creatures of truly staggering scale. Let's explore the four most promising habitats for giant alien life. 1. The void of space itself. 2. The deep oceans of exoplanets. 3. The dense atmospheres of gas giants. And 4. The strange ecosystems of extreme terrestrial worlds. Spaceborne megafauna, giant creatures in the void. We often wonder where all the aliens are, but what if they are just too big to miss? Could the real titans of the universe be lurking in the depths of space, waiting to be discovered? Maybe the reason we haven't seen the aliens is because we are looking for ships, when we should be looking for whales. At first glance, space seems like the worst place for life. No air, no water, extreme radiation, and deadly cold. But Earth has taught us that life is adaptable. If microbes can survive on the hull of the International Space Station, and tardigrades can endure the vacuum of space, why couldn't an entire ecosystem evolve to live among the stars? How could life survive in space? Space-dwelling megafauna would need to solve these three critical challenges. Energy acquisition. Without food chains, these creatures would likely rely on solar radiation, absorbing sunlight like enormous cosmic plants, or they might metabolize dust, gas, or asteroid materials. Movement. No gravity means no walking, and traditional swimming or flying wouldn't work. On asteroids, you have to grab and climb along, which is plausible enough. These creatures might also sail on solar winds, using magnetohydrodynamic propulsion, or even employ gas ejection, or systems akin to natural ion thrusters. Internal pressure and biology. Space life forms would likely have thick exteriors resistant to radiation and pressure loss, potentially resembling gigantic living asteroids with biological heat regulation and natural insulators like aerogels or vacuum pockets. Could space creatures form complex ecosystems? When we imagine life in space, it's easy to picture solitary leviathans drifting through the void. But what if entire ecosystems evolve beyond the cradle of planets? A true void ecology, as we've explored before, where species interact, compete, and survive together in the vast expanse. The power supply is there. Our own sun emits a couple billion times more sunlight than reaches Earth, and could fuel immense ecosystems or civilizations. Swarming creatures might fill the role of plankton, drifting through interstellar dust clouds or debris rings of ancient worlds, feeding on microscopic particles or harvesting faint sunlight. These spaceborne microfauna could form the foundation of a complex food web, tiny, numerous, and vital. Predators in turn might stalk these clouds, feeding not just on flesh but on energy itself, siphoning off heat, radiation, or scavenging organic compounds trapped in drifting ice and rock. Some might be slow, patient hunters, while others are fast-moving shadows darting between asteroid belts. Over time, vast biological structures could form, space reefs of unimaginable scale, like a natural Dyson swarm. Countless organisms might gather around a star, converting its energy into life. Clusters of living shells, solar-collecting membranes, and photosynthetic creatures could create shimmering, ever-shifting reefs, a cosmic equivalent of coral pulsing with color and energy. This is perhaps the least Earth-like but most fascinating vision of cosmic megafauna, not solitary giants but entire ecosystems of drifting life. Space whales, living reefs, translucent creatures trailing tendrils like jellyfish, whole communities surviving and thriving in the void, bound not by land or sea but by starlight itself. As immense as such creatures and ecologies can be, we will look at even bigger ones today. But first, let's consider some other places leviathans might dwell. Giant oceanic creatures, titans beneath the ice. The sea has always been a cradle for giants, but what happens when the ocean stretches 1,000 miles deep and never sees the sun? If there's any environment that naturally lends itself to giants, it's the deep oceans, vast, dark, and full of pressure, but also full of potential. Here on Earth, it's the oceans that cradle our largest creatures. The blue whale still reigns supreme, its mass supported by water's gentle embrace, but Earth sees our shallow puddles compared to what might exist elsewhere. Water is perhaps the most common molecule in the universe, after diatomic hydrogen and monoatomic helium. Whole worlds of water may have formed in the void, even long before rocky planets like our own became common. Many exoplanets and even moons in our own solar system may harbor subsurface oceans stretching beneath thick shells of ice. Places like Europa, Triton, or distant water worlds cloaked in kilometers of frozen crust. And beneath that ice, alien seas could run so deep their pressure dwarfs anything found on Earth. Yet paradoxically, those crushing depths might be where the largest creatures thrive. In these pitch-black abysses, freed from the constraints of gravity and surface weather, life might grow enormous. Massive filter feeders could drift slowly through the darkness, scooping up microbial clouds or chemosynthetic blooms near geothermal vents, in turn powered by tidal forces or atomic decay in the deeper core. Predator leviathans might roam these alien depths like silent submarines, powered not by sunlight but by heat and chemistry, the same forces that drive Earth's deep-sea ecosystems. Given that one of the lead candidates for the origin of life is in such dark and deep oceanic thermal vents, it would not be too surprising if every modest-sized icy moon of a gas giant or brown dwarf housed life. Without the need for dense skeletons to resist gravity, these creatures could be built of softer, more flexible materials. Gigantic balloon-like bodies filled with buoyant fluids might float effortlessly, their mass spread wide rather than packed dense. Think of jellyfish scaled to the size of mountains, trailing bioluminescent tendrils hundreds of meters long, pulsing through alien waters like drifting stars. possibly carrying their own ecosystem of smaller flora and fauna along with them, like the great mythological turtles with islands on their backs. Some might even interact with the ice shell above. Enormous creatures could rasp minerals from the ice, hunting for frozen nutrients, or use sonar-like calls that resonate through leagues of water and ice. Over millions of years, such life might evolve forms adapted not only to swim, but to anchor themselves to the frozen ceiling, dangling vast nets of tendrils down to the abyss below. And if those icy shells ever fracture or vent to the surface, such giants might breach into open water or even space itself, however briefly, perhaps become the basis for some future ancient sea monster myths in humanity's encounters across the stars. Or perhaps tendrils of life will reach up slowly and introduce some form of photosynthetic life to bring more energy and biomass to the dark sea below the ice. Here, size potentially becomes a major advantage. We know that surface area increases with the square of size, while volume, and thus mass, increases with the cube. Heat loss or transfer is primarily a matter of surface area, so a creature 10 times wider than another would have 1,000 times the mass, but only 100 times the surface area through which to lose heat. As a result, its base metabolism, if focused on retaining warmth, could run at just a tenth the rate per unit of mass, while still maintaining internal temperatures. This advantage grows if the creature can support a thicker skin or insulative outer layer, slowing heat loss even further, much like we often discuss with larger spaceships being able to carry heavier armor or radiation shielding. A slower metabolism saves energy, but comes with the trade-off of making the creature sluggish. Yet for something of truly enormous size, speed may not be necessary. Its sheer bulk might provide all the security it needs for most predators. Still, such creatures might not be entirely slow. They could possess long tendrils or appendages containing clusters of nerve centers, subbrains, similar to how an octopus operates. These could act quickly and independently, striking fast when needed while the main body remains ponderous. Alternatively, we might imagine a hive mind arrangement, with the Leviathan controlling swarms of smaller, faster creatures, fish or squid-like beings that hunt and gather for it. Perhaps they feed their colossal parent directly, or maybe, when the need arises, the giant simply consumes its own minions to sustain itself. In these alien oceans, life wouldn't just be big, it might be ancient, slow, and powerful. Entire ecosystems might form around geothermal oases, with the largest creatures migrating between them like cosmic whales between feeding grounds, their songless calls echoing through the dark seas for centuries. A realm where scale is measured not in meters but in megatons, and where the true titans of the universe might be hiding just beneath the ice. And while those icy oceans beneath frozen shells might be ideal cradles for leviathans, it is hard not to look upward from those moons and wonder, what are the gas giants they orbit? Could those vast, swirling worlds themselves be home to megafauna even greater in scale? Before we dive headfirst into the belly of a Jovian beast, let's take a moment to ask the real question. If you did find a space leviathan the size of a cruise ship in some planet's deep seas, how exactly do you bring it home? Answer: very carefully, and with a really, really big aquarium. That's the idea behind Fishbowl Starships, our latest exclusive. It's a speculative plunge into how future spacecraft might rely on water, yes, actual water tanks, to shield against radiation, regulate temperature, transport ecosystems, and even cushion against micrometeoroid strikes. Because sometimes the best armor in space is the stuff you put in your coffee. It's just one of the many oddball yet serious concepts we explore on Nebula, where every episode of the show airs early, ad-free, and often comes with extras that don't make it to YouTube, and by subscribing, you support the channel directly. No middlemen, no algorithm games, just more science and speculation. You can subscribe for just $3 a month with the annual plan, or grab a lifetime membership for $300, and never worry about renewals again, plus guest passes let you share the fun with friends. Just head to go.nebula.tv/IsaacArthur and join us for more tales of cosmic giants, whether they are biological, mechanical, or need aquariums the size of planets. Giants amid the clouds. Life inside gas giants. In the skies of gas giants, evolution might trade legs for balloons and wings for sails, and scale, quite literally, for the clouds. At first glance, gas giants seem hostile to life, colossal balls of hydrogen, helium, and volatile gases with crushing pressures and chaotic storms that rage for centuries. Yet they are also some of the largest potential habitats in the galaxy, their dense atmosphere stretching down for tens of thousands of kilometers. And where there is atmosphere, there is potential for life, especially life that floats. On Earth, the skies are home to creatures that drift, glide, and soar. If evolution can find a way to fill the skies of a rocky planet, why not those of a gas giant? Especially when dense atmospheres and thick cloud layers provide the perfect mix of buoyancy and energy sources. In the upper layers of a gas giant, where pressures and temperatures are more forgiving, we might find colossal life forms adapted to an eternal sky. Imagine vast balloon-like organisms, living airships the size of cities, filled with lighter-than-air gases like hydrogen or helium, drifting lazily through Jovian skies. Their buoyant bodies could maintain altitude, floating serenely between bands of clouds, absorbing energy from sunlight or feeding on complex organic molecules stirred up from the depths. They may even have flagella able to convert wind power into energy they can use. Some might even be filter feeders, drifting with the currents and sieving out microscopic life, air or plankton, swirling in the atmosphere. Others could be predators, using jets of gas or chemical bursts to stun their prey, their vast mouths opening to swallow entire swarms of smaller floaters. On Saturn, the gravity near the top is more or less the same as on Earth, and its thick atmosphere moon, Titan, has even lower gravity. But on Jupiter and bigger gas giants or brown dwarfs, gravity is far stronger than Earth's. On all of them, gravity rises as you go down, as does pressure and density. Perhaps most life here would avoid the depths, stay in the high, thin layers, where the pull and pressure is weaker. Yet for those that risk descending deeper, the rewards could be immense. The deeper layers might be rich in complex molecules or even prebiotic chemistry, offering a feast for those hardy enough to withstand the rising heat and pressure. And just as whales dive deep and rise again, these sky beasts might cycle through layers of atmosphere, sinking down to feed, then rising back to the gentler skies to rest and digest. They may use complex bladders to let them rise and sink like submarines, and thin membrane wings to let them glide around. Some might even generate their own lift by producing internal heat or chemical reactions, carefully balancing themselves against the pull of gravity. Electricity crackles through these skies too, with immense lightning storms flashing across the clouds. Some creatures might evolve to harness that energy directly, electrovores, feeding out the very lightning that rips through the sky, their bodies bristling with conductive spines or vast biological capacitors, storing stolen energy. Many such planets have rings created by impacts or moon collisions that often drop debris to the planet below, and such periods of high bombardment might fuel life to new heights as resources become abundant in the ash and nutrient burning up as those meteors enter the thick air. It's a realm where life might have no need for solid ground at all. Evolution could favor beings with no more concept of up or down, only currents, thermals, and endless skies. And a place like that, scale is limited only by the strength of the winds and the availability of the fuel. Given a thick enough atmosphere, there's nothing stopping a creature from growing as large as a mountain, or even a continent. And who knows, much like our deep-sea leviathans from earlier, perhaps some of these sky leviathans could even glow with bioluminescence, lighting up the clouds from within, silent drifting titans whose passing sparks auroras and sends ripples through the endless storms, home to entire ecosystems sheltering on top of them, or in their nooks and crannies, safe from the deadly wind. I think such behemoths would be a sight so wondrous that a visiting starship might mistake them for alien cities or floating ships, when in truth they are just life, vast, ancient, and utterly alien. If cosmic megafauna exists in gas giants, they may be among the hardest to find, concealed within those thick, roiling clouds, but if they do, they would represent one of the grandest triumphs of life's adaptability, creatures born not of land or sea, but of sky alone, forever adrift in the endless storms. Terrestrial kaiju and sandworms, monsters on land. Of course, not every giant needs to soar through alien skies or drift in endless oceans. Some worlds, perhaps even some like our own, might still give rise to true terrestrial titans. Planets with lower gravity, thicker atmospheres, or simply eons of evolutionary arms races could produce creatures that walk, crawl, or burrow across their surfaces like the great kaiju of fiction. And while Earth's own limits have kept such monsters confined to story and screen, alien worlds might be the perfect breeding ground for real-life Godzillas or sandworms. Every child imagines monsters stomping through cities, but on some worlds those dreams might walk, or crawl, or thunder below. Land is the harshest stage for giant life. There's no buoyant sea or thick atmosphere to help carry the weight, just the relentless pull of gravity threatening to collapse bone and muscle under the creature's own mass. Yet even here, with the right conditions, truly colossal life forms might emerge. I'm reminded of the sandworms of Dune, and that world of course is empty of moisture, water is hyper-scarce, and we might imagine some creatures develop large sizes in order to store water safely and efficiently. On low-gravity worlds, where weight is reduced but muscle strength and bone durability remain the same, the cube-square law loses some of its bite. Creatures that would buckle under Earth's gravity might stand tall, or crawl long, on worlds where gravity pulls only a fraction as hard. Add a dense atmosphere, rich in oxygen or other chemical fuels, and the stage is set for massive beasts to roam. Nothing prevents less massive planets from having thick atmospheres. Titan, for instance, has a thicker atmosphere than Earth, and Venus's atmosphere is thicker still. A strong magnetic field certainly helps by deflecting solar wind that would otherwise strip away atmospheric gases, but not every star has a solar wind as intense as our sun's. On some worlds, especially tidally locked planets, conditions might get even stranger. One hemisphere could be a scorching desert beneath an eternal sun, while the others remain a frozen wasteland cloaked in endless night. Between them, a narrow twilight zone might stretch from pole to pole, forming a vast ring of habitable land and sea, where the light is dim but constant. In such worlds, we might imagine colossal creatures, scaled-up versions of camels or sandworms, adapting across those brutal deserts. Perhaps they would carry vast reserves of water within them, venturing into the sunlit side to bask and feed, converting sunlight and stored water into the raw materials of life. Their waste and byproducts might sustain entire ecosystems in the harsh sun-baked lands, turning these desert wanderers into walking oases, feeding a whole web of life wherever they roam. Low-gravity critters might resemble towering sauropods or even kaiju, plodding behemoths armored in dense hides or mineral-encrusted plates, their every step carving deep trenches in alien soil. Others could be slow-moving mountain ranges of flesh and bone, evolving not to chase prey but to simply endure, feeding on vast forests or absorbing nutrients directly from the ground, like walking trees, or living, rolling glaciers of flesh and bone. And as with our oceanic moonkraken, they might have thin and fast tendrils with their own brains that could act far more rapidly than their immense main body implies. Perhaps the giants of such worlds won't walk, they'll crawl or burrow. On or beneath the surface, sandworms and tunnelers can avoid the worst of gravity's wrath, spreading their bulk across the Earth and using it for support. Here, size becomes an asset. Greater mass means greater momentum, allowing these creatures to punch through rock and soil, carving vast caverns in their wake. In lower gravity, sliding through sand is easier too, less weight holding things together. It might be a good place to hide from the day on a tidally locked world, too, and given they might have little tectonics from tidal locking, who knows how deep the sands might run on the sun side of such worlds. Burrowers might feed on subterranean biomass, or even tap into geothermal vents for heat and energy. Some might lie dormant for centuries, waiting for the right moment to erupt from the earth in a display of power that would make any kaiju proud. Entire ecosystems might revolve around these colossal diggers, with smaller creatures trailing in their wake, scavenging what the giants stirs up. Others might grow so large that their backs become ecosystems of their own, rolling hills or even forests sprouting from their armored hides, Their movements so slow that an observer might mistake them for land itself. Creatures, plants, and even civilizations could rise and fall atop such a mobile mountain without ever realizing it was alive. We often imagine this with the giant sea turtles whose shells sport island ecologies on them, but this could happen to a land life form too. Movement would be slow, deliberate, measured not in seconds but perhaps in seasons. But with enough mass and momentum, these giants would not need speed. Like glaciers with purpose, they would simply roll over anything in their path. And just as some of our myths imagined titans slumbering beneath the earth, these creatures might pass entire lifetimes underground, awaking only for brief moments when conditions are right, erupting in geysers of stone and dust that seed the surface with nutrients or even life itself. Whether striding across alien plains or tunneling unseen beneath our feet, terrestrial megafauna represent the ultimate in planetary scale biology. Life forms so massive they reshape the worlds they live on, not merely inhabitants of their planet, but forces of nature unto themselves. Megaflora, when the giants are green. Not every giant needs to move to conquer its world. Some merely grow, patient as the mountains themselves. Since we are contemplating life forms that might move at a glacial pace, let's consider life forms that might be flora, not fauna, or some alien version which is neither but not mobile, or not very mobile. While animals struggle against the relentless demands of mass, mobility, and metabolism, plants and plant-like life play by a different set of rules. Freed from the need to move, hunt, or pump oxygen to distant muscles, Megaflora can often grow to staggering sizes, especially in the right conditions. On Earth, the largest living organisms are not animals but trees, towering redwoods, ancient sequoias, and vast fungal networks sprawling unseen beneath the soil. Unlike animals, plants rely on passive energy collection, sunlight for photosynthesis, nutrients drawn from the ground or air, and they don't need to support heavy, moving muscles or brains. As a result, they can devote more of their structure purely to growth and stability. Their greatest challenges come not from movement but from gravity, water transport, and structural integrity. Even here, however, clever biological adaptations like vascular systems, lignin-reinforced cell walls, and hollow structures allow plants to push toward the sky. But what happens when we look beyond Earth, on worlds with lower gravity, higher atmospheric pressure, or abundant resources? The limits on Megaflora could stretch far beyond anything we know. Giant alien trees might rise like mountains, their trunks kilometers wide, and branches sprawling for miles, forming entire ecosystems in their canopies. Some might even be semi-sentient. They are neural-like root systems, processing information slowly over centuries, acting as the ancient memory of their worlds. In aquatic environments, we could imagine colossal kelp forest, each strand thick as a skyscraper, reaching from ocean floor to surface in kilometer-deep seas. On gas giants or Hycean worlds, floating Megaflora might dominate, vast balloon-like structures filled with lighter-than-air gases, drifting lazily through the clouds, harvesting sunlight while dangling nutrient-collecting tendrils below. The cube-square law still applies to Megaflora, but the absence of movement and the support of surrounding mediums like water or air allows them to scale far larger than animals. The threats are slower and subtler, gravity slowly pulling them down, storms toppling them, or droughts starving their roots. Yet given time and the right environment, it is often the green things, or their alien analogues, that grow to truly cosmic proportions, shaping the landscapes, seascapes, or even the skies of their worlds. And on some worlds, the largest living thing might not walk, swim, or fly, but stand, grow, and wait, patient as the mountains themselves, and perhaps easily mistaken for one. What if the very stars had hearts that beat, or the planets themselves were alive? Welcome to the realm of true cosmic megafauna. True cosmic megafauna, when worlds and stars are alive. As staggering as sky beasts and sandworms might be, they pale compared to the most extreme visions of cosmic megafauna, creatures so vast they blur the lines between life form and landscape, living worlds or even stars. After all, if the universe permits life on planetary scales, why stop at something merely big when life could be measured in megatons, megawatts, or even megalight years? Imagine a creature the size of a moon, its body a labyrinth of tunnels and habitats, supporting entire ecosystems within itself, a hollow world beast drifting through space, its skin a kilometer-thick layer of rock and organic composites, its blood oceans of liquid metals churning beneath. Civilizations might rise and fall inside such a being, never realizing they lived within the veins of something alive. Or consider a star beast, an organism whose biology is so advanced, either by evolution or advanced techno-organic engineering, that it taps directly into nuclear fusion, feeding out the raw power of its stellar heart. Its vast magnetic wings spread across millions of kilometers, harvesting energy and regulating its own fusion processes. To us, it might look like a star until it moves, or it may resemble a moving Dyson swarm. Creatures of such scale could live for eons, measured not in centuries but stellar lifetimes, their final death throes birthing nebulae, seeing new stars and planets in their wake. What if some stars are not born, but hatch? And this is just within our universe's familiar physical laws. If we dare speculate further into alternate realities where gravity is weaker, where the speed of light is different, or where the strong nuclear force allows materials vastly beyond our own, we could imagine life so large and strange it transcends even these notions. In such a universe, creatures might weave their skeletons from hyper-strong matter, denser than neutronium yet flexible as spider silk. The metabolic furnaces fueled not by mere chemistry, but by controlled fusion reactions, living suns walking across alien landscapes. Here, size limits imposed by the cube-square law or material strength would dissolve, opening the doors to life forms spanning planets, stars, or even entire solar systems. And perhaps intelligence itself might scale upward, boltzmann brains that emerge by chance as simple seeds in otherwise dead universes, and that grow vast as galaxies. Great clouds of self-aware gas, slowly calculating, dreaming across millions of light years. In this context, the very structure of the cosmos becomes a living thing, consciousness embedded in the dark matter halos of galaxies, or lurking the great voids between them. And if such things exist, they are not merely large, they are cosmic. They are not life as we know it, but life that strains the laws of physics, self-replicating, self-aware systems embedded in the very fabric of space and time. Perhaps they don't even recognize us as life, any more than we notice the cells beneath our feet. But even if such beings remain forever beyond our reach or comprehension, their mere possibility forces us to ask, how big can life get? Where does biology end and cosmology begin? And as we peer deeper into the cosmos, will we someday realize that the stars themselves are watching us back? Final reflections. Life without limits. The universe is vast beyond comprehension, and so too might be the life forms it holds. From drifting sky whales and burrowing sandworms to plant-sized beasts and star-hearted titans, the boundaries between creature, world, and cosmos begin to blur. Somewhere out there, life may already have found ways to thrive on scales we can scarcely imagine. Slow, ancient, and powerful, shaped by alien physics and unfamiliar rules. And perhaps that is the greatest lesson of cosmic megafauna. Not just the thrill of imagining colossal beasts, but the reminder that life is endlessly adaptable. It is not confined to the forms we know or the worlds we understand. Give it time, energy, and a place to grow, and life may fill every niche the universe offers, whether it's beneath frozen oceans, drifting through the skies of gas giants, or stretching its minds across the very stars. And whether it arises naturally or through artifice of technological civilizations, once human minds turning themselves into vast organisms of flesh, metal, or something altogether new, life may one day span scales better described as landscapes or solar systems than mere biology. Of course, for all we know, the Milky Way is just the mitochondria of some larger cosmic cell. In the end, we are part of that same story, a species that once huddled around campfires, now dreaming of alien leviathans, and pondering if entire worlds might someday stir and blink in the cosmic dark. We wonder not because it is likely, but because it is possible, and because deep down, we know that our quest to explore is driven by the same force that propels all life, the need to grow, to discover, and to imagine what might lie just beyond the horizon, because that is what life does. And so as we peer into the vastness of space, let's keep wondering, because whether we find monsters, marvels, or something stranger still, the journey itself will remind us that we, too, are life reaching for the infinite.